Welcome to Manish Kumar channel. So today we are going to discuss about kernel range of a linear transformation, and we will see dimension theorem, which is also known as the rank nullity theorem, and we will also look at when the transformation is 1 1 or on 2. Okay, so to know the definition of the kernel and range of a linear transformation, we can define like this. Let L is a linear transformation from one vector space to another vector space. The kernel of L is denoted by shorthand notation KER of L is the subset of all vectors in V that maps to zero vector of W, right? That is, you see, kernel is a set, right? Kernel of L is a set such that all those V's in V such that LV map to zero vector. Okay. And similarly, we can also define the range of L, or we can write range L is the subset of all vectors in W that are the image of some vectors in V. That means range L is equal to all LV for some V is in V, right? Okay. So if you want to see how to visualize it, so visualization is very clear. So if you see, this is a set, right, consisting of the points, okay, of the vectors. Okay, so all those points coming in the red circle which map to the zero vector of your W, right? So this is a linear transformation. So L maps all those elements, right, such that it becomes the zero vector of W. Okay, so all such vectors in the red circle will be forming a subset of V, right? And that is going to be the kernel. Okay, means after applying the linear transformation, this map to zero vector of W, all those such element, like if I say like this, all those such element which map to only zero vector, right? So if this map to zero vector, so this set which is a subset of V will be the kernel set. Okay, and we will also see that kernel is subspace of V. This is a very, very important result. Kernel of L is a subset of a subspace of V. Subspace of V means, first of all, it should be a subset. You can very clearly you can see that this is a subset, as well as that follow the two property, closed under addition and closed under vector multiplication. How do you prove the subspace in for a given vector space? The same way we are also going to do for this set. But this set is all those vectors V, in all those vector in V that map to zero vector. That set is going to be the kernel L. Okay. Now the result, let L be a linear transformation from V to W, then kernel L is a subspace of V, right? So how do we prove? First, first step, let kernel contains the zero vector. And we know since L is linear, so we know already L is linear, so zero map to zero vector, right? This is 0 of W. 0 map to 0 vector, right? So it means that 0 vector belongs to kernel. It means that kernel is non-empty. So this set is not at all empty. So this set consists of at least single element, which is zero element, right? Second property, what we have to show, second step, closed under addition. Let U and V belongs to kernel L. Then as per the definition, L of U map to zero vector of W and L of V map to zero vector of W, right? Now, what about U plus V? Since V is a vector space, U and V belongs to V, then their sum also belongs to V because of the fact that V is vector space. Okay, so U plus V is in V, and then now take L on U plus V. So since L is linear, this is linearity property. Since L is linear, L of U plus V is nothing but LU plus LV. And what is the value of LU and LV? 0 vector, 0 vector. That finally goes to 0 vector. So U plus V belongs to the kernel, right? We find an element such that this goes to 0 as per the definition of the kernel. So U plus V belongs to kernel. It means that kernel is closed under addition, right? Now the last step, this is closed under scalar multiplication. So take any U belongs to kernel and alpha be any scalar coming from the field. So alpha U is also is in V because of V is vector space, right? So now since L is linear, which is given to you, so L alpha U is equal to alpha times L of U, and which is nothing but alpha times of, and since U is in kernel, so L U map to 0 only, right? So that maps to 0, and 0 times any scalar quantity alpha will be 0 only. So it means that alpha U also belongs to kernel, right? This implies alpha U also belongs to kernel L. It means that kernel is closed under scalar multiplication, right? So for any subset V is a set, any subset W will be a vector subspace if W is closed under vector addition and W is closed under scalar multiplication, and W itself will be a subset of V. Then we can say that W is a subspace. Similarly, we have proved that this kernel is a subspace for a given V, right? So this is a proof. Okay. Now let us see one more definition. 1-1 map. So let X and Y be two sets, then F is a function from X to Y, right? Function or map, you can say. So we say F is 1-1 if distinct elements of X are mapped into distinct elements of Y. That means x1 not equal to x2 implies f of x1 not equal to f of x2, right? Or equivalently, if f of x1 is equal to f of x2, which implies x1 equal to x2. So do uh, you know these two results are equivalent, right? So now one more important result, 1-1 linear maps. So let V and W be two real vector spaces and L from V to W be a linear map or transformation. Then the linear map L is 1-1. We call it as this linear map is 1-1. It means that we can find two element x1 and x2. L of x1 equal to L of x2 implies L of x1 equal to x2. Or else x1 not equal to x2, L of x1 not equal to L of x2, right? So L is 1-1 if and only if kernel set is only 0 vector, right? So which we have to prove. Or if and only if L maps only the 0 vector of V into the 0 vector of W. This is the meaning, right? So L is 1 1 if and only if kernel contains 0 vector. If kernel contains 0 vector, then L is 1 1. Both way we have to prove. Okay. So this is very important result. So let us see the proof. So necessary part, suppose L is 1 1, right? And let any V belongs to kernel. Okay. Then we have to show that kernel contains only 0 vector, right? So since L is 1 1, L of V, and V is coming from the kernel, so which goes to 0 vector of W, right? And which is equal to L of 0 of V, right? L is 1 1. Since L is 1 1, so L of X equal to L of Y implies X equal to Y because of the fact that given that L is 1 1. So what we can conclude, V is only nothing but the 0 vector, right? So it means kernel L, this set contains only 0 vector of V, right? Sufficient part. So let kernel contains the 0 vector only, then what we have to prove? We have to prove that if L of V1 equal to L of V2, right, implies V1 equal to V2, right? So now what we do here, L of V1 equal to L of V2. I'm assuming only kernel contains 0 vector. Now we have to prove L is 1 1. Okay. So now suppose L V1 equal to L V2. Since L is linear, right? So I can take L of V1 minus L of V2 is equal to 0 vector of W, right? I am just taking other side. And since again L of V1 minus, instead of minus I can write here L of minus V1, right? V2, right? Because L of alpha X is equal to alpha L of X. So basically what I'm trying to say is alpha is equal to minus 1. So this minus goes inside because of linearity of L. L is linear, okay? And kernel contains only 0 vector. Then we have to prove that L is 1 1 also, okay? So now here since L is linear, so this can be written as L of V1 minus V2 as 0 vector, right? You got my point or not? So this part we achieve L of V1 minus V2 equal to 0 of W, right? And what is the property? If any vector goes to 0 vector, it means that vector must be in kernel. So this new vector V1 minus V2 is in kernel, right? And only kernel contains 0 vector, not other than any vector. So in this case, V1 minus V2 is just the 0 vector, right? And V1 minus V2 implies you can take other side V1 equal to V2. So we have started with L of V1 is equal to L of V2, and we concluded that now V1 equal to V2. So which implies L is 1 1, right? This is a very important result. So any linear transformation if you have and kernel set contains only 0 vector, then you can say that the linear transformation is 1 1. Okay. Now another important result, as you have seen, range of the linear transformation is a subset of all vectors in W that are the image of some vector in V. That means range of L means LV, V belongs to V, right? So now how do we visualize how the range looks like? So visualization, if you see V is a vector space and W is another vector space, L is linear transformation. So all those vectors sitting here, all those vectors sitting here, these all are looks like L of V1, L of V2, and so on. And V1, V2, all are in V, right? So that maps to here, that maps to here. All those V that maps to this range, right? This range V1, V2, and so on, and somewhere here, all those points coming from V, LV, such that V is in for some V is in V. Okay. So if you see here, this is again a set and of course subset of W, right? So as we have proved before, kernel is a subspace of V. Now we are going to prove that range is a subspace of W. That is again very important result. Okay, range will be the subspace here. So again, for proving subspace, W is a vector space, then subspace will be a subset of it, right? And then closed under addition and closed under vector addition, closed under scalar multiplication. That two property we have to show. Okay. So if you see here, L is a linear transformation from V to W, then range is a subspace that we have to prove. So proof, since L is linear, so zero vector map to zero vector always, right? This is always true. So 0 of W, we find a V, that is 0 of V in V, right? It means that zero vector belongs to the range, right? Because of the fact that the definition, all those, if you see the definition here, a range L is the set such that all those V, and since L, zero vector of V will map to zero vector of W, right? This is always true for a linear transformation. So you will always find a vector, you will always find this vector L of 0 V is nothing but W 0, right? So you will this set consists of this vector always, right? You got my point or not? 0. Okay. So this set is non-empty basically, we are trying to say, right? May contains more vectors, but linearity will produce at least non-zero set. Okay. So now if you see here, so hence what we can say, 0 vector of W belongs to the range of L. Thus range of L is non-empty. Okay. Assume W1, WB2 in two vectors in the range, then we have to prove that W1 plus W2 also is in the range. So for W1, we can always find L of V1 and L of V2 for some V1, V2 in V, right? So what about W1 plus W2? W1 plus W2 again is in W because W is a vector space. So which will be the L of V1 and L of V2? And since L is linear, so L of V1 plus V2. So we have always find out some vectors V1 plus V2 such that L of V1 plus V2 equal to W1 plus W2. It means that W1 plus W2 belongs to the range. It means that the range is closed under addition. Similarly, for any W belongs to the range, alpha be any real scalar, right? Coming from the field, then W can be written as L of V for some V is in V. Then you can just take alpha times of W is nothing but alpha L of V. Since L is linear, so alpha LV is equal to L of alpha V. Since L is linear, so L of alpha V is equal to alpha L of V, right? So this is the property we are using. So it means that alpha W belongs to the range of L. It means that L is closed under scalar multiplication. Therefore, we can say that range L is a subspace of W. Okay. Now on to map. We have already seen that one map. Now we are going to see another result on onto maps. So L is a linear transformation from V to W. We say L is onto if the range of L is equal to W, right? Range, it means if you see in this picture, this green circle is going to be equal to the big W, whole W. If this range L is equal to W, then map is onto. Then map is onto, right? It means that every vector, for every vector sitting in W, we can always find some element in V such that L of V is equal to that small w. So all members should be there, right? So it it means that L is onto if and only if, this is very important result, every vector in small w in W is LV for some V is in V, right? So now finding a basis for the kernel of a linear transformation. This is exactly, solving system of equation AX equal to 0 type, right? And which we have done before in lecture 1 and lecture 2, right? So 1, 2, 3, if you see solving homogeneous system of equation, solving non-homogeneous equation system of equations. So using Gauss elimination, Gauss Jordan, RREF, all those things we have done before. Okay. So now here what had happened, method for finding a basis for the kernel of a linear transformation, that is called kernel method. So what you have to do, let L be a linear transformation from Rn to Rm, be a linear transformation given by L of x equal to Ax for some m by n matrix A, and this matrix is unique with respect to the given linear transformation, which we have seen in the matrix of transformation. I can recommend the previous video to see. To find a basis for kernel L, perform the following steps, right? So basically the basic idea is A will be constructed m by n. So this m comes first as m, and then this n comes second. So m by n. This is how we represent the matrix. So now step 1, find matrix B, where B is the reduced row echelon form of A. So you know how to apply RREF and get to the B matrix. Okay. Then solve for one particular solution for each independent variable in the homogeneous system Bx equal to 0. Keep that reduced row echelon form matrix B x equal to 0, and the ith solution, let's say Vi, is found by setting ith independent variable to 1 and remaining all other independent variable as 0, right? Then this set V1, V2 and so on Vk is a basis for kernel L. Okay. And then if you find the dimension of kernel, that is going to be the nullity, we will see later. So we can replace any Vi with C of Vi, where C not equal to 0 to eliminate fractions. Okay. Similarly, range method, L is a linear transformation from Rn to Rm. Okay. And L of x equal to Ax, where A is a matrix m by n. To find the basis for range, perform the following steps. Again, you have to reach to the echelon form, right? So find B, which is a reduced row echelon form of A. And step 2 is that form the set of those columns of A whose corresponding columns in B have non-zero pivots, right? This set is a basis for range. It means you can just suppose you have a some columns, right? And you have reduced RREF, right? RREF, let's say, right? And you got pivot only here, pivot only here, first column and last column, right? Then corresponding to first column and last column, you keep in the basis set of the range. This is what they are trying to say. Okay. So another result, if L is a linear transformation from Rn to Rm with the matrix A, and we have seen that A is a matrix of transformation with respect to any basis of Rn and Rm, then dimension of range is equal to rank of A. Rank of A is nothing but the dimension of the range, number of non-zero pivot columns after reduced row echelon form. Similarly, the dimension of the kernel is equal to the n minus rank of A. How many variables are given? So n variables are given, so n minus rank of A. So now third one, dimension of kernel plus dimension of range is equal to dimension of domain L, which is n, right? So basically Rn, if you have Rn to Rm, and L is a matrix of transformation or linear transformation. So this n was broken into two pieces, n, and one is, let's say, k is rank, then nullity will be n minus k, right? Rank was subtracted from n. So this equation is satisfying as n, right? So rank and nullity. Rank plus nullity equal to dimension of the vector space, and that is known as dimension theorem. Okay. So now the dimension theorem. If L is a linear transformation from V to W and V has a finite dimension, then range L is finite dimensional vector space, right? And dimension of range plus dimension of kernel is equal to dimension of V, or rank plus nullity equal to dimension of V. That is known as rank nullity theorem, right? And one more corollary, if A is any matrix, then rank of A and rank of A transpose are equal, right? That we have already discussed in rank video. So let us do one problem. Let L from P3 to P3 be given by L of AX cube plus BX square plus CX plus D is equal to 3 times CX cube plus A plus B times of X plus D plus C. Okay, this is my linear transformation given to you. Now the question is this vector is, because this is P3, so dimension of P3 is 3 plus 1, right? So the P3 means all the polynomial of degree at most 3, right? And so in this case, including constant polynomial. So you see here, 3 degree polynomial I have, and which is transformed to a 3-degree polynomial. So L is a linear transformation. So you can verify L is linear. What you have to do? L of u plus v is equal to L of u plus L of v, and L of alpha u is equal to alpha L of u, right? So this property of linearity you have to do so. Okay. Now the question is this vector is in kernel? Why? Why not? So we have to answer yes or no. If not, then why not? Similarly, part B, part C, and part D. Is this vector is in range? Why? Why not? Okay. So let us do that. So solution. So part A, is this vector is in kernel L? Now answer is no. Why? To be in kernel, we must have a polynomial px that map to 0, right? 0 polynomial, right? Then let 0 polynomial looks like the structure will looks like 0 times of x cube plus 0 times of x square plus 0 times of x plus 0. This will be the shape of your 0 polynomial, right? So overall this becomes actually 0. If you multiply 0, 0, 0, all those become 0. Okay. So let px, this is the polynomial. So apply linear transform. After applying linear transform, uh, you will get to know what is a here 1, b is here -1, c is here 3, and d is here -1. So when you apply linear transform on p, you will get the coefficients, right? If you see the transformation, 3 times of c, 3 times of c into x cube, a plus b and d plus c. So these coefficients already you have collected. So 3 times of c, c is here 3. So 3 times of c, right? A plus b, a plus b, and c plus d, c plus d, right? This is the transformed value. Okay. Then 9x cube, and this becomes 0, and this becomes 2. So this is not a 0 polynomial, because 0 polynomial will looks like this. Everything should be 0. But here we are getting non-zero coefficient. So this does not map to 0 vector of w actually, right? It means that the given polynomial does not map to 0 vector of w. To belongs to kernel, it should map to 0. But this is not the case. It means that this vector does not belongs to kernel L, right? Similarly, second part, is this belongs to kernel? Answer is yes. Yes, this vector belongs to kernel. So this polynomial. So coefficients are again a is 1, b is -1, c and d are 0. So p of L of px is 3 times of c. 3 times of c. So this is 0. And a plus b, this is again 0, and c plus d, this is the transformation for L, right? So this is going to be complete 0. So it means px map to 0 vector. It means L of px equal to 0. This implies this vector belongs to the kernel L, right? Now we can see the analysis for a range C part. Is this vector belongs to the range L? Answer is no. And there is an explanation here. A polynomial px will be of this form in this range if there exists some polynomial in v, right? W, v and w, v and w, right? So L, v, all those LV such that v belongs to v will be the range set, range L, right? So now there exists some polynomial, let's say qx, which is of having the coefficient type ax cube plus bx square plus cx plus d, some bigger uh, alphabets I have chosen so that it should looks like a different, because both are the P3 only, P3 to P3, right? So to distinguish this is in B. So QX is here in B, basically I'm trying to say, right? So QX is here, right? QX, such that L of QX, L of QX will be that one, right? So QX is sitting here. So now what had happened here is L of QX, again we use that same transformation. So I got these coefficients, and then you can compare the coefficient with the given polynomial. So here 3c equal to 3. So it means c equal to 1. A plus b is equal to, there is no term of x. So we can assume a 0 times of x, right, in this polynomial. So that coefficient is 0. And now the c plus d constant term is minus 2. And since already you have c value, so you can calculate d value, right? But if you see in this transformed domain, no x squared term is appearing, right? Since there is 4x squared term, right, that cannot be obtained from L of Qx, right? So no polynomial satisfy this transform because of the fact that 4x square is no longer in the right hand side of the transform value, right? So this vector does not belongs to range L. You got my point? So this is what very important we have to think of. Okay, because we don't have anything to be compared with the uh, 4x squared term, right? Then part T, last part, is this belongs to range L? Answer is yes. We require QX. Again, QX is the same form with this coefficient, and try to collect the coefficient, right? Then A, B, C, D all are the here integers. So there exists a polynomial QX such that this equal to 3x cube minus 3x square plus 1, and implying that this belongs to the range, right? Now let us do one more important problem. For a linear transformation L from V to W, find the basis for kernel L and a basis for range L. So find basis for kernel L. Find the basis for range L. Is this map is 1 1? Is this map is on 2? Find the basis, find the dimension of the kernel, find the range of the kernel, and then verify the dimension theorem, right? These all are we have to do. Okay. So L is a linear transformation from R4 to R5, right? You got it. Then L is given by the matrix of transformation A will be of size what? 5 cross 4. M N, right? 5 cross 4. If you check 1, 2, 3, 4, 5 rows and 4 columns, right? So now for that, what we have to do, finding kernel L, to find kernel L, we have to solve Lx equal to 0. It means that we are going to solve Ax equal to 0. But A is given as 5 by 4 matrix. So we have to find reduced row echelon form on A, RREF. So RREF of A, if you solve the RREF of this matrix, you will get equivalent matrix this. So this is the RREF, right? Only 2 columns you are going to get, and remaining are no pivot you are going to get. Okay. So in that case, rank will be 2 basically, right? Non-zero pivot column in the reduced row echelon form. So rank is 2. Okay. So now we want to solve this system, right? So this system bx bx is equal to 0 we are trying to solve. So to solve this system, x1 minus x3 and plus x4 equal to 0, and x1 x2 plus 3x3 minus 2x4 equal to 0, like that we have to solve. So we, after solving this, we are going to get two equations, right? And in that case, if you see here in this pivot, uh, the non-pivot columns are this, which is corresponding to x3 and x4. So x3 and x4 is treated as free variable, right? Free variables. So now what had happened here, if you see, after solving this in terms of x3 and x4, we are going to get this. Free variable, I mean independent variable. They can take any value. They all are going to take any value, whatever they like, right? So here, the solution will be of the form x1, x2, x3, 4, which is nothing but x3 with 1, 3, 1 minus 3, 1, 0, plus x4 minus 1, 2, 0, 1. And then you can say that these two vectors are the basis while setting x3 is 0 and x4 as 1 and x4 as 0, x3 as 1, right? Once you set it, you will get these two columns, right? So basis for kernel is 2, okay? So number of element in the basis is 2, so nullity will be 2 basically here, right? Similarly, finding the range. So how many pivot column we are going to get? Corresponding to those columns, retrieve the columns of the original matrix. If you see in this, corresponding to after RREF, we got two columns, right? And retrieve this original column from the matrix. That will be your uh, basis element for the range L. Okay. So pivot column corresponding to uh, the will give you two vectors, right? So basis for range is these two are the basis. Okay. So now the question is checking whether 1 and 2 and dimension theorem. So dimension of kernel is equal to 2. Just now we have seen one result. L is 1 if the kernel consists of 0 vector. Kernel L, this set. So now kernel contains 0 vector. Okay. All those, this set consists of 0 vector only, right? So in that case, dimension, what is the dimension of this? Dimension of this will be only 0, right? Because this vector is linearly dependent, so it does not forms a basis, right? Because any alpha times 0 vector is going to be 0. So linear combination goes to 0 and alpha is non-zero also, right? So this does not comes under the basis, this vector. Okay. Therefore, basis has dimension 0 only, right? So if L is 1, then kernel contains only 0 vector and then dimension of kernel is 0, right? But here we are getting dimension as 2. Hence, the given map is not 1, right? Similarly, dimension of range is equal to 3. And we know if dimension, this is W, right? And if that range is going to become whole W, right? Then you can say that the dimension 3 is not equal to 5 because the transformation given to you from from R4 to R5, right? And dimension of the W is what? 5, and dimension of range is 3. So 3 not equal to 5. If dimension of range is also equal to 5, then we can say that this map is onto. Just now we have seen a result before. So this is not an onto map also, right? Now let us verify the dimension theorem. Dimension of range L and dimension of kernel is equal to dimension of V. So dimension of range L is 2, dimension of kernel is 2, and dimension of the V vector is 4. So 2 plus 2 is equal to 4. So this verify the dimension theorem, right? Let us do one more problem. L is a polynomial. L is a linear map from P2 to P4 defined by L of Px equal to Ax square Px. So what is a kernel L? What is a range L? Verify dimension theorem. Okay. So finding kernel, the kernel consists of all polynomial P which belongs to P2 such that L of P equal to x square into Px, and that map to zero vector, right? Because of the fact that it belongs to kernel. Okay. This means that the only possibility of this to be zero, either Px will be zero for all x or x equal to zero, right? Then, so the only polynomial in kernel is the zero polynomial, right? Only polynomial will be only the zero polynomial. Okay. Thus, kernel consists of zero vector. Then in that case, just now from the previous problem, in that case, dimension of kernel is 0. Okay. Dimension of kernel means we are finding out the basis for kernel, and basis means the number of element in the basis is known as dimension, right? But zero vector cannot be in the basis because zero vector is linearly dependent. And you know, a set is said to be basis if it is Li and it spans whole space, right? So this zero vector is not at all Li. Therefore, the dimension is 0 for the kernel. Okay. So finding the range, the image consists of all polynomials of the form such that LP equal to x square, that this polynomial of degree 2, and that gets multiply becomes degree 4. It means that range consists of polynomials with x square as a factor. So range L will be this polynomial where A, B, and C are coming from the real field, right? So what is the basis for this range? If you see, the basis for this range is x square, x cube, x4, right? Hence, the dimension range. What is the dimension? And you can prove these sets are Li. And range L will be subspace of W. You have V, you have W, right? So uh, range L will come here, range L, and range L consists of your, the polynomial of degree 4, right? So which belongs to P4, right? So range L is contained in P4. Okay. So which will be having the element x cube, x4, and x square. So now these sets are Li, and also dimension of the range is 3, right? You got my point or not? So what is the dimension? Linear transformation was given from P2 to P4, right? P4 means The dimension is 5, right? But range only covers 3, not 5 dimension. Okay, so this is a subspace actually. Okay, then verify the dimension formula. Dimension of kernel is equal to 0 and dimension of range equal to 3. So since P2 is a space of all polynomial of degree at most 2, so the dimension will be 3. So you can say dimension of range plus dimension of kernel equal to 3 plus 0 equal to 3, which is the dimension of P2. So thus rank nullity theorem holds. Okay. Now we will see when we say that transformation is 1 1 and onto. So definition, L is a linear transformation from V to W, and we know if L is 1 to 1, if and only if distinct vector in V have different images in W. That we have already seen as per the definition. So L of V1 equal to L of V2 implies V1 equal to V2, and onto L is onto if and only if every vector in the codomain W is the image of some vector in the domain V. That means L is onto if and only if every W in W there is a sum V is in V such that LV equal to W. So nothing will be left over in W. So entire range becomes the your W actually. Okay. So there is an important result. V and W be vector space and L is a linear transformation from V to W. Then L is 1 1 if kernel contains 0 element, right? 0 vector. If and only if, or in other word, if and only if dimension of kernel is equal to 0. That we have already proved. So we are summarizing the result. And if W is a finite dimensional vector space, then L is on 2 if and only if dimension of range L is equal to dimension of W. That is also important result we have seen before. Okay, so from this 1 1 and onto we will develop an isomorphism kind of stuff in the next video. All right, we will require these definition again. Okay, so this is very important definitions. Now we have also seen that V and W be vector spaces and L is a linear transformation. Then L is 1 to 1 and T is a linearly independent subset of V. Then L of T is linearly independent subset of W. That is also very important result. And if L is on 2 and S spans V, then LS spans W, right? So let us do one more problem. Which one of the following linear transformations are 1 to 1? Which one are onto? Justify your answer by using row reduced echelon form, right? And determine the dimension of kernel and range, right? So L is a linear transformation from R2 to R3 given by L of x1, x2 is equal to this. So this is your matrix A. You have to perform RREF on this matrix, okay? And solve AX equal to 0. After applying RREF, let's say equivalent matrix is B. So you have to solve BX equal to 0 to get the kernel, right? So now again, second problem. So let us do one by one. So transform matrix A is this. Find the kernel, AX equal to 0 we have to solve. So to solve this AX equal to 0, we need to first find the reduced row echelon form of this. So reduced row echelon form after RREF. And I recommend to see my previous video on RREF to know how to find the RREF, right? So this is the reduced row echelon form, and we have two pivot columns, right? Pivot columns, okay? Then dimension of kernel is equal to 2 minus 2 because all those things are going to be in the range only. Number of non-zero pivot columns are, 2. So range will be 2 basically. So L is, and dimension of this, because n minus rank is 2, so 2 minus 2, because we have started with R22, 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 R3, and 2 can be split into 2 can be split into 2 plus 0. So all the dimension was in uh, range, not in kernel. So, and we know L is 1 1 if and only if kernel contains only 0 vector. So this is 1 to 1. L is 1 to 1. Now find the range. Since rank of A is 2, but the codomain has dimension 3. From R2 to R3 we have defined, right? And W is actually R3. So since dimension of range is 2 only, not equal to 3, so this map is not onto, right? In a similar fashion, we can do on second problem. So solve Ax equal to 0, find the reduced row echelon form. Again, if you see, rank of this matrix is 3, right? So kernel has 0 vector only. Okay, so L is 1 1. Range uh, of A is 3, rank of A is 3. So dimension of the codomain. So dimension, we have given the problem 2. If you see the problem 2, from R3 to R3, right? So 3 can be written as 3 plus 0, right? So this is rank and this is nullity. Rank means dimension of range, right? And nullity means dimension of kernel, right? Range L, you can say. L is a linear transformation, right? So since this is 0 and this is 3, so range of L is equal to range dimension of W. 3 equal to 3. So this map is onto, right? So this, the second map is onto, right? So this is 1 1 as well as onto both. Then we will see 1 1 onto is known as an isomorphism, and that we will see in the next video. Okay. So now let us do one more problem. The matrix of linear transformation with respect to certain order basis for the domain and codomain is given. This is the matrix from P2 to P2, right? Determine whether the given linear transformation is 1 1, 1 to 1, and 2. Justify your answer using reduced row echelon form to find the dimension of the kernel and range. So all those part you can do. So first we have to reduce this matrix into reduced row echelon form, and we got, after reducing, all 3 columns are non-zero pivot elements. So rank will be 3, and then range of the kernel will be 0, right? So kernel has 0 dimension, okay, and rank is 3. So dimension of kernel is n minus 3. So 3 minus 3 is 0. So this map is 1 1, 1 to 1. Only kernel contains 0 vector, and also the range of dimension of P2 is 3, right? Dimension of P2 is 3. So dimension of range is equal to dimension of W, right? So this map is also onto. So thank you very much. Thanks a lot.